Swayam Prabha. Digital India. Educated India.
Welcome to this discussion on embedded software design and validation. Today we are going to discuss about the model validation part. So far we have talked about the design concept in context to embedded software, and we have seen this design is mostly divided into two parts. One is the modeling of the design and then final implementation. We have mostly so far focused on the modeling part and discussed that in detail, taking the reference of finite state machine. There are different other types of modeling also, but as of now we are focusing on the finite state machine type of modeling, and with that example we are going to discuss today the concept of validation. Now, the validation mostly means whatever we are doing in the design step, whether that is the correct or not, like given some specification, when we are taking that to implementation through in between modeling step, what is the guarantee of the correctness. So, for that this validation step is important. So, today we shall mostly discuss about what we mean by validation, what will be the steps of validation in brief, and while we are talking about final state machine, whatever we have discussed so far, in that context what will be the steps, what will be the main points where we shall focus when we are talking about validation. Okay. So, this is the same the textbook we are following now is Embedded System and Software Validation by O.P. Choudhury, the published by Elsevier. Okay. Now, in case of validation, the concept or the validation meaning is the determination of the correctness of the final program or software produced from a development project with respect to the user needs and requirements. This is the general direct definition we get for validation. Okay. We will see what are the steps we have to follow when we are talking in context to embedded software. Okay. So, when we are doing the validation of embedded software, in general we need to verify each and every stage of our design. Why we need validation to be specific in embedded software scenario? Because mostly we are talking about critical systems, safety critical systems. Why we are talking about embedded controllers, or we are designing CPS systems, or we are putting embedded controllers on that CPS framework, the applications what we take, maybe that is automotive, maybe it is medical, in general those are safety critical. Okay. So, when we talk about some high safety critical or most safety critical systems, we can take the examples of automobiles, transportation, flight, nuclear power plants, medical devices, etc. Some devices like our daily household devices, mobile phones, smart TVs, they are also the example of CPS, where we actually use embedded controllers, but they may be less safety critical, but whatever may be the design, safety guarantee of correctness is a major requirement when we are designing this kind of embedded softwares. So, that is why we need to have some step, some guarantee that whatever we are designing, they are as per the what is our requirement, and they are also following some safety critical requirements that may be coming through our specification, or maybe during our design we are adding them considering the requirement of the application, okay, considering the weight of the application. So, with this, when we were going to discuss about validation part, there will be few important and common terminologies we will be going to use repeatedly. So, first in this introductory discussion of validation, we will first introduce them, try to understand them properly, so that we can take them in detail in our later discussions and next day discussions. So, these terminologies are testing, simulation, verification and performance analysis. Let us take them one by one. So, as the testing definition suggests, testing refers to checking that a system behaves as expected for a given input. So, few important points to note: we are giving some particular input or set of inputs to be specific, and we are testing them on the system. So, here the system being checked can be the actual system. When the actual system in execution, we can actually give the test input and we can check whether each and every requirements according to our specification, given noted specification, they are getting satisfied or not. Okay. Then comes the term simulation. Now, we should keep this testing and simulation side by side. Why? Because it is very important to note that when we are talking about testing, we are talking about actual implementation. In some cases, we may not have the actual platform in hand. So, simulation also suggests to running a system for a given input, but the system being simulated may be a model, because so far whatever we have discussed, FSM, that is a model of the actual system. So, it is simulation of the model, okay, of the actual system. In simulation also, we take the model of the system, we give some set of inputs and check if everything is going fine or not, and in general we check for the functionality. We will see that when we are talking about embedded software design, embedded system design, when we are talking about correctness, there are two important points to note. First of all, correctness means, of course, in a straightforward way, the functionality correctness, like whatever specification given, according to that the functionality of the implemented system is is actually producing the same functionality or not. But when we are talking about embedded scenario, safety critical scenario, that is not all. In this case, we also need to have timing verification, because we have in our introductory lectures, we have already talked about how crucial the deadline is. The deadline is an important factor. We have also talked about hard deadline, soft deadline, where in some cases the failure of meeting the deadline, that may be catastrophic. So, in this case, whenever we are talking about verification, validation, these terms in context to embedded software, we need to keep in mind this is not only about the functionality, this is also about the timing verification. But when we are talking about simulation, we are simulating the system model for some given inputs, we are mostly focusing on the functionality part. The execution, come to the next point, the execution platform on which the system is being simulated is different from the actual execution platform. So, the platform may be different, and the benefit of simulation is that if we do not have the actual platform, still we can actually check whether functionality wise our model is correct or not. The execution platform on which the actual system will be executed may not be available, or it might be getting decided through the process of performance simulation. That means, let us consider we are simulating our model on different platforms. And we already from our specification we have some deadline bound, and we are checking after implementing in these different platforms which implementation platform will be suitable to take this design or the final implementation forward. On which implementation platform if we implement, we can actually meet the deadline and the timing requirement can also get satisfied. So, that way these are the two important benefits of simulation. First one, if we do not have the platform in hand, still we can check the functional validation. Number two, if we do not know which platform will be suitable to implement certain specification, we can actually simulate the same same model on different platforms, and we can check where we are getting the deadline satisfied timing, where we are getting some deadline which is beyond the within the threshold which is actually meeting the deadline. So, that way we can actually choose the platform. Next point, typically a software model of the execution platform might be used for performance simulation. Okay. So, when we are taking the functional validation is our prime thought, but along with that when we are choosing certain platform that may or may not be our final platform, but from there we are getting some idea that what may be our timing requirement if we go with that particular platform. From there we can get some idea that which can be our final platform. So, these are the important benefits of simulation, and from there we can typically understand the difference between simulation and that prior testing. In the testing part we need to have the actual implementation and the actual platform. There we are taking given inputs and then we are doing the final testing. Okay. So, first with the model we do simulation, then at the implementation level when we have the actual platform, then on the actual system we do the testing. These are the major differences. Next comes the term. So, we have discussed testing, we have discussed simulation. Next comes the term verification. Now, when we are talking about verification, we generally meaning formal verification. Now, formal verification, to understand formal verification, first we need to understand what is the limitation of testing and simulation. So, from the whatever we have mentioned before in the prior slides, if we observe, we see that we have mentioned one important point for both the cases, this given input. Here also given input. So, for both the cases we are choosing some inputs, and that inputs how the system is reacting or the model is reacting for that given input. Based on that we are doing some analysis, but that may not consider all type of possible inputs. That may be a huge set, but there may be we are missing some amount of given test inputs. So, we need some mathematical guarantee that we are exhaustively we have considered all type of inputs, and here comes the importance of formal verification, which gives a mathematical guarantee. So, let us follow the points in the slide. Formal verification refers to checking that a system behaves as expected for all possible inputs. Okay. Exhaustive testing is inefficient or even infeasible. That means exhaustive testing, it may happen we are missing some test cases. In that scenario, we may not covering those test cases, and when the system is actually getting deployed, maybe those cases are creating problems. So, either it is inefficient, it may take huge amount of time to execute to get the result, or it may be even infeasible. There may be some man-made mistake, there may be some missing of test inputs. So, all are possible. So, that is why formal verification methods gives strict mathematical guarantees about the functionality of the system, which gives the which ensures that okay, we have considered all possible inputs. Okay. So, all these previous three whatever we have discussed, they are mostly coming in context of functional verification. We are covering all type of functionalities and we are covering all type of maybe some critical points in terms of functionalities. But on top of that, as we already discussed, that we need to have performance confirmation. That means we need to have some strict guarantee about performance. What do we mean by that? When embedded software means few set of instructions, and those are embedded on the bigger system as a control. Now, the execution time of all those instructions, there should be some upper bound, and the effect of those execution, like if it is finally giving some input to some actuation, then all these tasks should be completed within a certain deadline, and that deadline bound scenario must be validated or verified through this performance analysis. Okay. To employ mathematical analysis techniques for estimating performance. Okay. So, this is the difference between these four pillars. Those are combining together, getting combined together to form the whole concept of model validation. Okay. So, when we are talking about this model validation, starting from testing, simulation, then model checking, and then finally the model checking basically refers to the formal verification, and then the performance analysis. So, all this point we will discuss in brief detail. Okay. So, from this discussion maybe it is clear that when we are talking about validation, it comes in at different levels. That means, it is not only that we can get satisfied just by validating or verifying the model, or it is also not the case when we have completed everything, modeling, then designing, implementation, everything, and we have the final system in hand, then only we are starting this validation step. That is also not the case. So, when we are preparing the system model, we are doing this model validation. Then the model should be implemented based on the requirement. Maybe it is some part of it may be implemented on hardware, some part on software. Once that is done, if there is a need of this hardware software co-design, there are some part of the implementation is going to the hardware end, some part is going to the software end, then there must be some communication between the outputs, between the processes, so that we can get the final output. And when there is some communication, we also need to have this kind of communication validation. That means, it is not only the model validation, it is not only the implementation validation on a particular platform, it is validation in any and every platform wherever any part of the system has been employed, has been implemented. And then comes the communication part, when we have multiple platforms, multiple processes actually getting executed on multiple platforms. then we need to validate the communication part also. And these are the discussions that where we are going to validate. The next point comes what we are going to validate, and there we have also discussed that this is not about the functionality. Functionality is of course important, given the specification we need to have all the specific points to be included in our implementation. But along with that, we should have, along with functionality, we should have performance validation also. So, that is why when we are talking about validation, it is not a small concept, or it is not a particular concept for a particular platform or particular stage of design. This is basically to be done in different parts of the design, different platforms where the overall system is getting implemented, and this is not of course restricted to only functionality or only timing. All of this concept should come together. So, we have different levels and we have different types of validation that we are going to discuss gradually. Okay. Now, we should understand briefly what may be the complications in functionality validation. First of all, if we now remember, if we just quickly recap a bit about whatever we have discussed with our FSM concept, finite state machine concept, we have seen the concept of hierarchy. We have seen there may be some small FSMs, sub FSMs, some local FSMs, we may term them, and we can combine those local FSMs, let us say A and B, these are the smaller FSMs, and we can combine them together and we can get one level up hierarchy. Also within that, it may happen there may be some similar concurrent FSMs, they itself can have multiple own states or substates. So, that means whenever we are going to the higher levels of design, higher level means we are considering the top part of the hierarchy, not the granular part, the top part of the hierarchy, and we are considering that in terms of functional validation. In a simpler way, we can tell if we are checking the higher levels of hierarchy, and we can ensure that if my higher level functionalities are working fine, then I can assume okay, lower level functionalities are also working fine, and that is getting reflected in the combination in the higher level. So, in that scenario, what is happening when we are at the higher level of the design, then the complexity or formality in this, the word is used here, the formality of functional validation is getting reduced. When we are at a lower level, at the granular level, we need to consider all sub FSMs, all the smaller processes which is getting encoded to the sub FSMs, and together we have to separately we have to consider them, then we have to integrate them, we have to consider their communication, we have to do that validation, and gradually we can move up to the hierarchy. So, in that case we can with this concept actually we can actually explain this graph on the right hand side. We can actually see that as the level increases, level of details increases in the design, when we are at the granular level, then the formality or complexity of functional validation is very high. As the level of details are increasing, that means we are going to the upper level of the hierarchy, we are considering more abstraction, and there this formality of functional validation is actually decreasing. Okay. So, that is the same thing shown here, reflected in the graph. Okay. So, embedded systems are constructed at different levels of details. For functionality validation, the higher the level of detail, the lower the formality of validation method. Now, this concept is exactly opposite when we are talking about timing validation. Okay. In timing validation also there are different submodules and their communication, and that should get reflected in the timing part. So, often incorporate hard or soft real time constraints, okay, that we have already discussed. We know the meaning of these terms, hard and soft real time constraints. When we are going to the upper level, we need to consider the interaction of the system with its immediate and next immediate environment. So, there are much more complexities coming into picture, and that is why as we are at the lower level, we are basically focusing on a particular block and what is happening, what are the instructions getting executed for that block, and maybe what is the timing requirement. So, the accuracy is much less because we are not considering, the formality is also less and the accuracy is also less because we are not considering the effect of other blocks. We are also not considering the delay. It may happen the block we are considering is, we are just considering at the initial level the execution time for the code specified for that block, but we are not considering the communication delay if that block is basically waiting for some input coming some other blocks, and that will be governed by the overall communication delay present in the system. So, that way if we just focus at the granular level, lower level, our accuracy may be not so correct, whereas if we increase the level of the design, we can check the effect, gross effect of multiple sub FSMs. We can take the effect of the hierarchy, we can take the effect of the concurrency, buffering, etc., many more types of constraints, and then we can actually define actually get the idea of the accurate timing requirement. So, these are the complications when we are talking about functional validation and the timing validation. These are the differences basically. So, the same thing is just summed up here, that formal verification of functionality is better conducted at higher levels of abstraction. As we start considering lower level details, formal approaches do not scale up. So, those approaches we will see that in more detail when we will go for model checking, and there we go for general testing. Okay. For performance validation, as we consider lower level details, performance estimates are more accurate. That means, if we consider the details, but we are not restricted in the details on the sub part. As we start from the lower level and we just grow up to the high levels considering all type of constraints and delays, then we get more accurate timing. Okay. So, that will guarantee the correctness, that okay, for timing wise whatever we are getting, that is also within our deadline or satisfying our deadline or not. So, now with this we have understood that what type of validation or verification I have to do. Next, we will take the example of finite state machine, just revisit the concepts whatever we have discussed, and we have to check that at which points we have to consider these modeling techniques. Okay. So, how to validate FSM based modeling? We are going to answer this question. We are basically trying to get the idea that what are the levels where we will be actually considering these validation techniques. So, just to recap, we have already discussed this, that the finite state machine, the structure though we have discussed actually the 5 tuple general representation of finite state machine. Mostly we have 3 important members when we are defining the finite state machine. One is a state, and that way the hierarchical representations, the blocks, they should be verified, they must be validated separately, because timing wise, functionality wise, they may not be same. Okay. So, the challenge here, corresponding to the different levels of hierarchy, the notion of unit step also changes. So, the same thing, the granularity will also change. Just take that whatever we have discussed with an example, so that we will understand better where is the challenge in our verification or validation. So, here we have taken one simple example of light controller. Now, this light controller is having 2 states, on and off. This off state is simpler, but this on state can again have 2 substates, one is dim and one is bright. Again, this bright state can have 2 substates, one is stable and one is flashing. Okay. And if it is stable, there is no change, and if it is flashing, there is a self loop. There is a change of state maintaining some self loop. So, maybe some conditions may be here, that when the light controller we move from on to off, dim to bright, etc. But for the sake of simplicity, we are not considering that. Those are there, just consider. So, the point is, whenever we are going for these kinds of hierarchy, we can understand these substates and these substates, they are different. So, per hierarchy, the unit steps are different, their challenges are different. So, they need to be verified or validated separately to get our accuracy in terms of performance and in terms of timing also. Okay. Similarly, here is one example of concurrency taken. Okay. Now, this concurrent system is basically the example of centralized air traffic controller, which is having multiple clients, multiple client processes and some WCP or weather control panel. So, in simpler words, this air traffic controller is having multiple sub FSMs together. So, we can see here the some sub FSMs are shown, the clients, WCP and the centralized controller, because the air traffic controller is having one central controller. So, the ATC is basically the centralized controller. And when we are talking about concurrent FSM, the final output of this FSM, we have to consider the outcomes of all these FSMs, or how are they affecting one, how one of them are affecting the other. So, that way when we are talking about concurrency, basically the challenge here, we need to verify each and every FSM and their intermediate combination. Otherwise, what will happen? Here one example is shown for a system. If we just take the combined states, so ultimately the output states, output changes will be the combined effect of these sub FSMs, right. If we take that way, then let us say for a simple example, if we consider 2 FSMs or 20 states, then together they can generate one global FSM of 20 cross 20, 400 states. But what we are doing for the sake of simplicity, sake of simple visual representation, we are taking separately, validating separately these separate FSMs, where we are just considering 20 plus 20, 40 states, and then we are validating the communication between them to ensure the whole global FSM is working fine rather than handling huge number of states. So, control flow in each process, basically whatever we have talked so far, like of an overall gross system which is having two sub processes, and each of the sub processes are having 20 states each. Okay. So, now all this control flow in each process can be encoded as an FSM, and we can take them separately, separate FSMs, and we can actually check what is the combining effect, whether the combination communication everything is going fine or not, to ensure that whole global scenario is working fine. So, for that what we need to do? We need to do the interleaving of these FSM outputs. Now, if the interleaving is totally arbitrary, then that will be the one way, but that is not a practical case, right. So, now we have to think how we can do interleaving formally for different sub FSMs. How can we do the interleaving formally, the communication formally, to better understand or better validate the gross FSM. For that we need to actually validate. This is not about validating only the unit steps or the hierarchy or the concurrency, whatever we have discussed so far of the FSM part. It is also the necessity to validating the inter-process communication, the communication between two FSMs, to validate that part. So, when we are talking about this control flow of these separate processes, they are getting mapped or they are getting encoded as FSMs. So, when we are talking about that, local FSMs denote individual threads of control, and their composition is defined by interleaving. Now, we need to understand how can we validate, or at least we should have the clear idea about what is happening during this communication. Okay. That what we are actually communicating and whether they are working fine or not, to understand the gross scenario. So, here we take the composition of communicating FSM, that means now we need the communication and their validation. For that, for this validation, we generally define some action names. That means we label the transitions with some action names. Okay. These action names are defining some kinds of transitions. Now, when we are talking about two concurrent FSMs or two communicating FSMs, it may happen the actions, those whatever we are defining, they are completely disjoint, there is no overlapping. Okay. So, in that case we can actually do this kind of arbitrary interleaving, that is fine if these alphabet sets are totally disjoint. But if the action, this action is, there is some common actions between these two FSMs, let us say M1 and M2. Okay. These are the action alphabets of two different FSMs, and there is some intersection. Then we have to ensure, due to this communication effect, that those actions are only taken when this those transitions are only taken when the common action is getting satisfied. Okay. For action levels that are local to certain to some M1, okay, it is sufficient for only M1 to make a move. Sorry, M1 and M2, those are basically the two FSMs, okay, not the alphabets. So, these two FSMs M1 and M2, if they are having some common action alphabets, common actions defined, based on that the transition will take place, then the transition will be only taken when this common action is getting satisfied. If for local FSMs these actions are disjoint, okay, or restricted to that local FSM, then only one of them, either M1 or M2, can make a move. Okay. So, let us understand this whatever we have discussed so far with one example. So, when we are talking about, that means communication between FSMs, these FSMs M1 and M2, they communicate over these common actions. When they are actually depending on some common actions for some transition, then we term them as they are communicating, or they are communicating FSM. So, just take this with some formal representation. Okay. So far, whatever we have discussed in our general concept or general definition of FSM, we have considered state, okay, initial states and the transitions. So, this is for M1, S1, I1, and the transition 1 for M2, S2, I2, and transition 2. When we are talking about communicating FSM, we are adding one extra parameter, see, alpha 1 or alpha 2. So, these are defining the actions, the action set of that particular FSM. And if they are communicating, then we are also considering this alpha 1 and alpha 2, union alpha 2, this is the action alphabet. Some of the actions are defined for M1, some of the actions are defined for M2. Maybe or maybe not, there are some common actions. If there are some common actions, we know the transition, there will be some transitions defined on those common actions. If there is no common actions, totally disjoint, then we will be going with the arbitrary interleaving. Okay. So, this is how the representation works. Now, come to this transition part, transition relation, and see how, what is the difference with our previous concept of finite state machine. So, here we are having these actions. Any action A we are defining, that is coming from this set, union set, and we have some states defined. The S dash is from, belongs to S1, that means it is coming from FSM M1, and T dash S2, just see this previous S2, it is coming from M2. So, this relation, okay, this is a valid transition, that means ST to S dash T dash. Okay. That holds true if and only if any one of the following condition holds. Okay. So, there are possible 3 conditions as we have already discussed. Okay. So, this S dash, based on this action, a transition from S to S dash, that means transition in M1 is a valid transition, and T to T dash based on this same action A, that is a valid transition for from the transition set of M2. Okay. That is one condition possible. Okay. That means we are taking a, this is the condition of some common action. Okay. Otherwise, there must be some actions that is coming from this difference, alpha 1 minus alpha 2, from this difference set. So, that means from this relation we can understand this action is very much specific to M1. So, based on this action, only the transitions will be taken in the M1 part and not in the M2 part. See, that is why only the transitions define S to S dash based on this action A, and this transition is coming from the transition set specified for M1. Similarly, from the next condition alpha 2 minus alpha 1, from this difference set, if this A is the member of this difference set, so the transition based on this action A is only defined for M2. See, T A T dashed. This is the only valid transition for M2 part. Okay. So, this way we define the communicating FSM, where some actions are for the local FSMs and some actions are for the communication, okay, general, shared by both the FSMs. So, we just take this with one very brief example, where we have considered two local FSMs with two states, okay, idle and busy. Okay. If we go by our normal representation of FSM, we are basically getting here 2 into 2, 4 states. Okay, these are the combinations. But see, in this figure A, there is no action defined. But when we are defining the communicating FSM, we are considering some few states, and along with that, we are basically considering some actions. So, these transitions are possible when these actions are true, and this action data or this acknowledgement summarizes a communication across the two processes. Okay. So, when this data is coming from this idle to busy state, there is a general state representation or state change. Okay. So, that means we need to understand, when we are validating our communicating FSM or communication part of the FSM, we also need to understand what we are communicating, what to communicate. So, to communicate, each action symbol can be complex structure with one or more parameters. So, when we are communicating, it is not, may not be a simple communication, there may be multiple parameters. Okay. And these communication may be different for different cases. We will take example of synchronous communication, and also we will take the example of asynchronous communication, where in synchronous communication we know everything is driven by clock. Here this communication maybe if we consider this is the communication and these are the actions defined. Okay. The action level data represents a common action. Okay. And this data is also taking some parameter, particular value. So, as we are mentioning, this action level may not be simple. So, it is also taking the value 5, and it is taking that information and changing the state to idle to busy. Similarly, for this busy state, it is also sending the acknowledgement. So, this symbol is the denoting the sender, and this symbol is denoting the receiver. Okay. So, this one, for this state, this is a receiver of this acknowledgement signal and sender of this data signal. Okay. Similarly, for this this idle to busy, the separate cases may happen, but in case of synchronous, this is one example where we are showing the action level, it is not very simple. Again, when we are talking about asynchronous communication, see the change. In this asynchronous communication, we are not only talking about the sender or receiver part, sender or receiver actions. We are also need to define some extra action that is related to the buffer. This is one example of the defining the buffer process. See, in the first buffer process, okay, the state chain is from 0 to 1, 1 to 2 and so on. Okay. So, if we see this P this is PQ, this symbol implies this is a communication between P and Q along with some buffering process in between. So, the same action with this symbol is supposed to be a communication between a process P and Q. However, in the presence of stateful buffer process, it is a communication involving P and the buffer. So, P and Q, though it is a communication, but with the intermediate sign that indicates there is some intermediate communication with the buffer. For that, we need to also incorporate some action or action level for buffer. Here see, this defines the action level for buffer. Okay. So, whether we are buffering the communication from buffer P to Q or Q to Q, etc. Okay. Also, when we are talking about the sample process, see the states of the sample process. The sample process P or Q, they are having the communication, this P is having the communication is with Q, but with some intermediate buffer. Similarly, there may be some acknowledgement in between, but considering the presence of the buffer. Okay. So, based on the type of communication we are making, the type of action level will change. It may get more simpler to complex, and but the benefit of this action level is that when we are actually using this communication FSMs for our modeling, there may be a possibility of huge blow up of states in general representation. With this action levels, we are reducing those number of states, and we are also moderating and verifying, validating the communication part of these FSMs. That is very important when we are taking the general representation of CPS, complex representation of CPS. So, with these examples, we have understood when we are talking about validation, especially the validation of FSM, what are the points or what are the parts we have to take care of. We have to take care of unit step, but that is not only sufficient. We have to also take care of hierarchy, we have also take care of concurrency, and when coming to the concurrency or hierarchy, we have to take care of communication separately and efficiently. So, these are the points we have discussed for just FSM model validation. Now, the next question comes how to do that and what is actually happening when we are actually doing the testing, simulation or the formal verification. So, this part we will be taking in our subsequent lectures. Next day we will be talking in detail about simulation and testing, what happens and what are the limitations of them, of course, and gradually we will include the formal verification in our discussion. So, this is the reference, the same book, and the diagrams are most images are also taken from that same book mostly. So, that is all for today. Next day we will again continue our discussion on simulation and testing part. Thank you.